Welcome back, everyone. Today we've got a seriously fascinating explainer lined up for you. We're looking at a brand new piece of research that finally bridges a massive theoretical gap in one of the most fundamental algorithms we use in computer science. It's a 2026 paper called Decision Tree Learning on Product Spaces by Mokhar and their team over at the University of Maryland. Okay, let's dive right into this.
So, here is a bit of a mystery to hook you right off the bat. If you're a data scientist or an engineer, you already know that our absolute favorite machine learning tools, the ones we're deploying in the real world literally every single day, often completely defy deep theoretical explanation. I mean, they just work, and they work incredibly well. But for decades, the rigorous mathematical proofs explaining exactly why they work, they've been lagging far behind, leaving theoreticians in a state of mild panic.
Section 1. The Decision Tree Mystery.
To really understand this mystery, let's think about the top-down greedy heuristic. You know, the engine behind classic algorithms like ID3, C4.5, or CART. It basically works by iteratively growing a tree from the top down, just greedily picking the best feature to split on at each step. In practice, it's fast, it's intuitive, and it is highly interpretable. But, well, here's the catch. Older mathematical proofs could only guarantee that this worked under what's essentially a frictionless vacuum condition. They assumed our data came from a perfectly uniform distribution, kind of like a perfectly fair coin flip. But we all know real-world data doesn't actually look like that. It's messy, it's biased, it's heterogeneous, it exists in arbitrary product spaces, so the old theory just completely failed to capture our practical reality.
Section 2. Escaping the uniform distribution.
And that brings us to the actual breakthrough. The authors of this 2026 paper finally cracked the code. They extended the math to actually encompass these arbitrary product distributions. To quote the paper directly, our main result demonstrates that the performance guarantees hold even without the structural convenience of the uniform distribution. Basically, the theoretical math finally, unequivocally matches the messy practical reality we actually work in. Your favorite heuristic doesn't just work by accident on your biased dataset anymore, it works because it is fundamentally, mathematically sound.
Section 3. The math behind the magic. Now, to appreciate what they pulled off here, we need to look under the hood a bit. The very first key concept is called influence. Imagine you've got a dataset, and you're trying to predict an outcome. The influence of a specific variable is just the probability that if you were to re-randomize that one specific coordinate, the overall output of your function would change. It is, mathematically speaking, the ultimate measure of a variable's relevance. And finding the variable with the maximum influence, well, that is exactly how the greedy algorithm decides to split a tree node. So when analyzing the structure of the tree, the researchers realized they had to look at two competing forces. First, we have maximum depth, denoted as d-opt. Think of this as the longest possible reach of the entire tree. And second, there's average depth, denoted as delta-opt, which represents the typical path an everyday input takes. Tracking both of these metrics simultaneously, instead of just staring at maximum depth like the older theories did, is the massive improvement that completely unlocked their new proof.
So the crucial point is their core theorem. It actually proves that the size of the tree generated by this greedy heuristic won't just spiral out of control. Notice how it is tightly constrained by an expression that contains the exponential product of the average depth, the maximum depth, and the logarithm of the error tolerance. Basically, the tree stays totally manageable.
This mixed dependence on both average and maximum depth is just a brilliant, highly elegant solution. Contrast two extremes for a second. In perfectly balanced trees, both depths are relatively small, so obviously the math holds up fine. But what about highly unbalanced, comb-like trees? The maximum depth there is huge. It literally grows linearly with the variables. If the formula only relied on maximum depth, the math would absolutely blow up exponentially. But by multiplying that large maximum depth by the tiny constant average depth, the final product stays in check. The math gracefully handles even the absolute worst-case scenarios.
Section 4. Building a practical algorithm. Heavy theory is wonderful, sure, but how do we actually use this in the real world? Well, the authors spawned a totally tangible tool directly from their math, which they call Algorithm 2. And this brilliantly illustrates one full iteration of that practical top-down heuristic. Recognizing that the real world relies on finite samples rather than perfect, infinite probabilities, they built an algorithm that operates entirely on sample estimations, all while maintaining completely rigorous statistical confidence.
Breaking down these 3 specific phases, it goes like this. Step 1. The algorithm searches for the best leaf variable pair to split using estimated influence scores drawn from a sample set. Step 2. Once a split is chosen, it partitions the existing stored samples right down into the new child leaves. And Step 3. To ensure the statistical math doesn't just break down as the tree gets deeper, it draws fresh, new random samples from the distribution and adds them to the leaves.
Now, why is this so incredibly powerful for a data scientist? Because it is entirely parameter-free. Seriously, you don't need to guess the optimal tree size in advance. You don't need to know the optimal depth. It is fully 100% sample-driven. It just adapts and runs perfectly, figuring out exactly how many samples it needs at each and every step to guarantee an accurate result.
Section 5. Proving it with data.
Of course, bold theoretical claims require hard empirical evidence. Now, what's really interesting about this slide is the tracking of tree size across totally different distributions. If you compare the performance on a perfectly uniform distribution against a heavily biased non-uniform one, something amazing happens. Across both completely balanced target trees and highly unbalanced ones, the recovered tree size stays beautifully, cleanly constrained. The trajectory stays relatively flat, even as the error tolerance shrinks.
To summarize the data here, the algorithm succeeds exactly as the theorem predicted. The tree size stays remarkably close to the ground truth target. As you increase the dimensions, the size only grows mildly. There is absolutely no exponential blowup to worry about. And the sample complexity, meaning the number of queries it actually needs to make, remains strictly polynomial. For us, that means runtimes are completely manageable for actual day-to-day machine learning practitioners.
Which brings us to a rather provocative final thought. This research definitively proves that the greedy heuristic works for Boolean product spaces, features that are just zeros and ones. But could these exact same bounds, utilizing average and maximum depth, unlock the very next frontier? Could we soon see similar rigorous proofs for continuous features and threshold-based splits, exactly like what CART uses for complex numerical data? The theoretical gap is closing fast, and the tools we use every single day are finally getting the mathematical respect they actually deserve. Thank you so much for joining me on this explainer. I really hope you found this as fascinating as I did. Keep learning.